Swayam Prabha. Digital India. Educated India.
To day 6 of this lecture series, this Gyan course on basically microstructure and diffusion correlation in high entropy alloys. Just to remind you of last week, most of the time this is the situation we are facing, right? We have a material, and even if we have annealed it basically to death, meaning that the material will not show any longer over reasonable time scales any time dependence, we still have grain boundaries normally. We have a polycrystalline material, we have dislocations, we have outer surface. So it means that we have always microstructural variability. All the defects contribute to all properties. Some properties are dominated by the defects, especially grain boundaries and dislocations when we think of mechanical properties, but also electric properties, magnetic properties. Whatever you think of as a property is going to be affected. There are also higher order defects, like when you have grain boundaries meeting, intersecting. Then what do you get? You get from the intersection of two-dimensional defects a one-dimensional defect, a triple junction or a quadruple junction, depending on how many grains come together. In equilibrium, we would think normally of having triple junctions, so all of them coming together, and if the grains are having the same material, then the angle between them would be 120 degrees. But very often that's not the case, because either we have more than one phase present or we have still residual strain in the lattice, and then we can also have 4 grains coming together forming a quadruple junction. Now, after we discussed diffusion basics last week, what would you think would such a triple junction, so the junction, the line defect that connects 3 grains, so it's, if we look at the cross-section, basically a point, but in reality it would again be a quasi-one-dimensional defect, pipe. Would you think this is having different diffusion properties as compared to a dislocation? It might be. In the literature, actually, there have been reports going actually from much less energy, specific line energy of the triple junction as compared to a dislocation. There have been reports on the opposite, that it's more. It's a huge discussion over many, many decades. When you normalize this specific line energy with something like a grain boundary energy, always for the unit length or the unit area, so that you get just an energy and not per, then people have termed this as either positive or negative triple junction excess energy. And so far it has not been solved, but our results indicate that actually it is what you indicated, that it's not so much different from dislocation pipe diffusion. Maybe a little enhanced, so it's between or going between grain boundary diffusion, dislocation pipe diffusion, and there you're absolutely correct. it could be different for different systems. And then also the local stress distributions play a big role. But also these are important microstructural elements, because the triple junction basically govern how grain growth and coarsening would happen, because they basically need to move out in order for the grain, one of the grains becoming larger. And often these are the pinning points for the grains because of segregation of impurities inside of the triple junctions, and so they basically create what we call a Zener drag. So it means that impurity atoms are going to the defect find energetically low-lying positions, and so it's requiring a higher activation enthalpy to move these atoms out of their current position. So when we have all this, maybe you just remind me what we discussed last weeks. How do we now do a diffusion measurements when we basically apply tracer everywhere here, and then we section macroscopically? So what's the trick in experiment to analyze this complex situation? We slice the part, but then we have in each slice we have grain boundaries, we have part of the dislocation pipes, we have parts of the triple junctions, and so on and so on. Everything is also in the slices, because the slices will be not on the atomic scale, right? So they will be either micrometer thick or maybe a few tens nanometers thick, but still large with respect to an individual atom. So how do we distinguish them? Because we basically then count all the tracer atom in this slice, right? But then we count all the tracer atoms in the slice. How do we know whether the tracer atom has diffused along a grain boundary or along a dislocation pipe or just in the grain interior? The trick is to choose the temperature and time wisely, meaning that when you go to low temperatures, short times, only the fastest diffusion pathways will contribute to the macroscopic dimensions we require in order to measure diffusion, and this is how we can sort out. We can do because this is actually real experimental data from our group on diffusion rates in polycrystalline silver. And there you can see that basically we have a good contrast between volume diffusion, between dislocation pipe diffusion, between grain boundary diffusion, and between surface diffusion. Right? So it means that if you now choose a specific temperature, let's say this temperature, for a given annealing time, you will not be able to measure volume diffusion. It's just too slow. You might encounter dislocation pipe diffusion and grain boundary diffusion. And surface diffusion we take out because we cut the outer surface. So whatever diffused we cannot prevent, but we take out a sufficiently thick part of the outer surface of the sample so that it's not longer affecting our measurement when we put the slices into a detector to count the radioactive atoms.
When we say that like dislocation, diffusion to dislocation. Like during measurement, it will add up like dislocation, diffusion to dislocation plus diffusion to grain boundary.
Everything adds up, yes.
So it's like adding up, like it's not purely diffusion to dislocation. It's plus DG.
We always can only measure everything. So unfortunately, yeah, when we go to the slices, this is the macroscopic. This is the macroscopic slice. And we measure all the radioactive decay products in the entire slice. Each slice on its own, but for each slice we cannot distinguish any specific position where the tracer atom was sitting. And this is why all of these processes contribute in principle at the same time. But the good thing is, because of this dependence, we take out the surface, so we don't need to worry about surface diffusion. We are at temperatures maybe that are too low and the times for diffusion annealing too short. So volume diffusion cannot contribute because the diffusion distance, the effective diffusion distance would be one lattice constant or so. So we don't.
Like here the axis is Tm by T. In previous all case we take 1 by T.
Yes, good question. I give the question back to you. Why is that?
To find a homologous temperature.
Yes, maybe you can explain your colleague why is that important.
So based on that, where the temperature, how much is the temperature, where the material sustains. Like, so there we, with respect to that,
Very good. So it's exactly right. The materials processes and their kinetics depend on temperature, but for different materials, it's not really the absolute temperature which plays a role, but the absolute temperature normalized by the melting temperature of the material on the same absolute temperature scale. Because as I told you, 0.5 of the melting temperature, so a homologous temperature of T divided by Tm equals 0.5, would be the homologous temperature where we see that the diffusive processes become recognizable. And the same is true for recrystallization, for dislocation, motion, and annihilation. All of these happen with very different materials at similar homologous temperatures, even though the absolute temperatures can be quite different. Think about taking tungsten and taking indium or tin, right? The melting temperatures are so hugely different. So we can, if we want to do a diffusion measurement in tungsten, tin is already in the liquid state and maybe is evaporating already a lot, right? But on the same homologous scale, half melting temperature, we can still compare. And this is why it's very meaningful to always plot diffusion coefficients also for on a homologous scale, because that will tell you if the order of magnitude diffusion coefficients at a certain homologous temperatures are reasonable. So let's go to how to really measure. There is a couple of methods which are used, and I will be mostly talking about this method. And that's because you can see that this method has the beauty that we can cover a huge range of diffusion coefficients. So we can measure diffusion coefficients as low as maybe 10 to the minus 23 and as high as maybe 10 to the minus 8 square meters per second. No other method can cover such a wide range. Also, the sensitivity of this method will be the largest of all different diffusion measurements or methods. But sometimes we have to take other methods also into account, either if we want to measure in very thin sections, very close to the surface, and many people who are doing surface science worry about these issues. So they will be using something like Rutherford backscattering, RBS, or Auger electron spectroscopy. So if you want to measure proper surface diffusion, these methods are your friend. And then in between, there is electron microprobe analysis, EPMA, or secondary ion mass spectroscopy, SIMS, often in a time-of-flight mode, TOF SIMS, time-of-flight, secondary ion mass spectroscopy. And these methods are used whenever we cannot apply a radioactive tracer. So if we have stable tracers, then we can take the sample anywhere and use any method we like in order to investigate it. And then it's also possible to do SIMS and EPMA measurements. This we have to do for some elements where there is no good tracer. What is a good tracer, by the way? A good radioactive tracer. Good radioactive tracer needs to have a half-lifetime which is sufficiently long so that we can apply it, go through all the steps I'm going to show you in a minute, and in the end still have enough tracer left in the material so the detector can still count the decays. So if you have only, let's say, a lifetime of half an hour, after half an hour, half of the applied tracer will be gone. It's not longer radioactive. And after another half hour, again, half of the half is gone, right? So you have left only 1/4. And so it means that very rapidly you can then run into a situation where your counting efficiency is not sufficiently high to really recognize tracer or tracer profile over a certain depth. The tracer lifetime is one thing, but also the efficiency of the decay should be high. So it means there should be in the tracer enough activity so that you have enough decays per second so that the detector can give you a decent count. Otherwise, you have to wait just too long. And typical, what you have to do is wait maybe between something like a day up to 4 weeks of one slice in the detector to get enough counting efficiency to have sufficient signal to noise ratio. More is more or less just not done because so many people want to use the detectors and it just cannot take years or so to count, right? It's just a practical limitation. We have thus to select or to think of selecting two things, the method which we use, as well as the temperature and time we apply beforehand to have the tracer diffuse in our material. Because we need to estimate how deep is the penetration profile, how far can the tracer atoms diffuse into the material. Is this something like micrometers or is this something like nanometers? And this will then determine which method you have to use, because you need a certain good number of points in the diffusion profile to make a mathematical fit. And it means that your method needs to be able to slice sufficiently thin sections if your diffusion profile is small, has a small depth, and it can be more coarse if you have a large diffusion depth. Obviously, you also need to think ahead of time when you want to apply temperature and time, how many of the diffusion pathways you have. So if you want to measure dislocation pipe diffusion, you better have a material that has a lot of dislocations inside, so you get many tracer atoms that can diffuse along the short circuit diffusion pathways. So if you anneal out your material close to the melting temperature for a long time and then try to do dislocation pipe diffusion, maybe it doesn't work, because you could not wait long enough to get decent counting statistics. And so this all needs to be planned ahead of time with some trial experiments to get some experience of what's the typical diffusion rate. You need to know the microstructure, and then you can do very good diffusion measurements by the tracer method. So in the following, we will mostly talk about self-diffusion. Interdiffusion would basically take the same methods, because of the higher diffusion coefficients, some of these conditions are not so critical for interdiffusion. When we use radioactive isotopes for tracer diffusion, there is basically 4 different methods to obtain sections. And by far the most used ones are either mechanical sectioning, so you use a microtome and you cut slices. This is when you have a very long diffusion profile, so that each slice can be having micrometer dimensions in terms of thickness. Or if your diffusion profile is of the order of a few microns only, so your cuts have to have a thickness of, say, several tens nanometers. 100 nanometers maybe is a rather more realistic number. And then one can do parallel precision grinding to remove layers of the material, which you do when you grind and polish, right? But then in this case, the material which is grinded off or polished off is collected and then put into the detector. And the other one, which is very often used, is ion beam sputtering. So you basically shoot with ions on the surface, you sputter off atoms from the surface, so you create a sputter crater, and you collect the sputtered off atoms onto some foil, which again is then put into the detector. So this will be for something like then if you have non-radioactive isotopes, mostly secondary ion mass spectroscopy, spectrometry is used. And I will not talk about Rutherford backscattering or Auger electron spectroscopy, because these are really surface sensitive methods which are not really related to the topic of this course. So this is how the tracer technique works in principle. You have a material, this is the gray part, and you have polished it to very nice finish. Then you apply a tracer solution. It means you dissolute your tracer atoms in a solution, and then you apply it by a micropipette or so on the surface. You let it spread. Maybe you also do some rotation so that the spreading is more even. Then you let it dry. typically by a lamp furnace. And then you do the diffusion annealing. So you put the whole material, maybe wrapped into a protective molybdenum or tungsten foil, into purified quartz glass tube, which is filled with very pure argon, or you could use any other inert gas, put into a furnace, and the temperature is controlled very accurately over the whole time of your diffusion annealing. And this is set for a certain temperature, so you get a diffusion annealing done for a given temperature T and a time small t that you select. Then you take it rapidly out of the furnace so that the sample gets to room temperature as quickly as possible. Then you take off the external surface to don't get any impact of the surface diffusion that also occurs. Then you slice thin slices. Then you count for each slice the radioactive decay products, which are proportional to the number of radioactive tracer atoms in each layer. And then you plot it basically as a function, as some function of the depth. And this function of the depth will vary depending on whether you are measuring in the regime where volume diffusion is dominant, or where grain boundary diffusion is dominant, or where there is both contributions affecting your result, or also if dislocation pipe diffusion would be a dominant or also major mechanism. Yes? Haha, good. You saw it. There are two effects. This is the typical way a diffusion profile you gain looks like. And this could be related to having two mechanisms contributing. In the B regime, you have volume diffusion, which is slow, giving you the first part of the profile, and grain boundary diffusion, which is much faster, giving you the long tail. One possible explanation. Even if you have these two contributions, you would see an additional contribution, the strong decrease initially, because that's the grinding in effect. So if you basically polish your material to a certain section to get the first section, this polishing has already created some stresses and moved additionally some of the tracers into the next layer, and so on and so on. So you get this grinding in. And this is not only for grinding, this would also be true for the sputtering. So it means that one has to take this into account when one evaluates diffusion profiles. I will also show this later to you, because you basically have to subtract a zero profile in order to get out the grinding in effect, and just then process the artifact-free diffusion profile. So it means that you have to go through quite some steps in order to make a good diffusion measurement. The position of tracer, you have to buy the tracer at some point. It comes normally in solid form, then you dilute it in some suitable solution, which you then dilute further with double distilled water. Then you apply a certain specific radioactivity, typically 5 to 10 kilobecquerel on the surface. You need to watch the half-life time of the isotope you need. And you also need to know which decay pathway this specific radioisotope is doing, right? Whether it is emitting beta or gamma radiation. There is a third radioactive decay product. When radioactive isotopes decay, they could either go through a beta decay or a gamma decay. The third option is an alpha decay. But normally, and we and nobody else is using alpha decay isotopes because they are so dangerous. They can really harm you and create a lot of damage in your cells because of, and that could lead then to cancer, right? So this is why alpha decay tracers are not used for the measurements, only beta and gamma. Then there is an important point here. You need to check your material for macroscopic and percolating porosity. What means percolating porosity? It means when I now have, let's say, a cross-section of my material, and the tracer was initially here, and maybe I have a grain boundary here, but then I have maybe a pore and an interconnected crack, another pore, crack, another pore. Then this is defining a percolating pathway for diffusion. So it's interconnected. And that means within this percolation pathway, it's open surface diffusion which rules, which is much faster. So we would get basically the wrong answer out. We want to measure grain boundary diffusion, but we measure is surface diffusion because they are internal surfaces and not grain boundaries. In order to do this, we normally apply a gamma emitter on the sample surface, and then we just let it dry. And basically, we do not do any diffusion annealing. Still do a sectioning, because if there is open surface diffusion, the tracer goes into these open surfaces and along the percolating pathway. And when we then do sectioning and measure the isotope concentration in the depth profile, we see a result which comes not from diffusion, because we didn't anneal. So it means then we know, the sample is porous. We cannot use that sample for diffusion measurements. It's actually also a very sensitive way to probe for porosity, which is obviously very important also for mechanical properties, because you can determine something like 10 to the minus 4, 10 to the minus 5 fractions of porosity, which is difficult to do in any microscopy-based analysis. So, but this needs to be done. When you're sure there is no interconnected porosity, then you do diffusion annealing, as I just said. If you want to use short annealing times, typically less than 1 hour, then you need to do an annealing time correction, because the time the sample needs to get to the temperature and get back to room temperature then is considerable compared to the annealing time. And so it means that you have an undefined diffusion during the heating and during the cooling stage, which affects the outcome of the sectioning and detection. Then you reduce the material in diameter to remove the effects of lateral and surface diffusion. You do the serial sectioning, and then you use nuclear counting methods to measure the specific radioactive activity. And then you have to go through the mathematics of fitting the profile. So this is then starting from the very coarse profiles. So it means you have now maybe annealed your material up to high temperatures for a long time. So volume diffusion was really dominant, and you get a diffusion profile which is maybe 100 micrometers or so, or maybe more in depth. So you take your sample, which is an embedded sample as shown here. Right here. So the gray thing is the sample. And then first you do the reduction, meaning that you have a sharp blade which moves back and forth, so you can basically reduce the diameter of your sample by the sample turning quickly and by basically cutting off the edges, so to speak. Obviously, you need to do this in a thickness which is thicker than the average diffusion length into your material, because otherwise the solutes could go along the surface and come from the backside or from the side of the sample entering your volume. If you have done this dimensional reduction, then you can use a microtome with a sharp blade, preferably a new diamond blade, and then basically cut, right, by slicing over the top of the sample. You slice off a certain thickness, you collect it, and then you move the sample up and slice again with the same thickness. And so you get n number of slices. All of them separately go to a vial. They are again dissoluted. And then you basically count the radioactive decay occurrences over time. If you have a less thick diffusion profile, you basically go for the parallel grinding method. Again, you use then a sample, typically it's then rotated on a rotating holder to basically cut out again the sides for avoiding lateral and surface diffusion. Then you put the sample here in plane geometry, and then you have basically a very precisely adjustable grinding device, which grinds off thin section of your material, and you collect always everything which has been grinded off your material. So you grind off a certain thickness, you stop, you take off the grinding foil. The grinding foil goes to the vial, gets dissoluted, and the material grinded off is on the grinding foil or grinding paper. And so you basically collected all the atoms in that slice which you have taken off. How to determine the thickness? It's thickness. Yes, exactly. By weight loss. No, it doesn't like to. So it means you basically have to have a very good microbalance in order to calculate or in order to measure the weight loss coming from grinding off very thin slices, right? So it means that your accuracy of the scale should be of the order of 0.01, 0.001 micrograms. Then you can do it. Still, the sample will be totally weighted, and the sample is probably up to a weight of 2 to 3 grams. So there are not so many micro balances which can do this job. So you have to basically pay a little bit more to get a good one. But then it's a very simple and reproducible method to measure the thickness and again do these tracer analysis. If you have an even less thick diffusion profile, you go for ion beam sputtering. So basically you have a sample here situated on the sample holder, right, so around here, and you then shoot with ions on your sample. They sputter off atoms from your sample. You collect them here, and this is basically like a camera. Not a digital camera as today, but a very old-fashioned film camera. So it means there is one film which you expose now with the atoms sputtered off your material for a certain time. So you know that you have reached a certain depth of your sputtering crater. And then the camera moves the film to the next position. Then you start again sputtering, again for the same time. And so you get a long film where on the positions on the film, you basically have the sputtering profiles arranged according to their depth. Shallowest depth in the beginning, deepest depth in the end. Then you cut the film again, each part is dissolved, each part is put in a vial and then put into the detector, and you count again the radioactive decay products. And this is then how these diffusion profiles are obtained. If you have now very short-lived isotopes, then it's difficult, right? I mean, you can only rush so much with all these necessary steps. And then you can go to a large-scale facility. So everybody in the world has the right to apply for beam time. And this is at CERN in Switzerland. And this isotope separator online device is called Isolde. We built it at this place, and it's usable by anybody who applies and who gets beam time granted. And basically what you do is you create very short-lived isotopes by implantation. So they are coming from a nuclear reactor, like for example, copper isotope, radioactive one. It's implanted by this beam here in your sample. And at the same time, then you can sputter, you have to do the same as just said, sputter off your material, and then it's detected again here. And you have here the sputter film automatically moving forward and going across a detector, so that you get basically online diffusion profiling, because everything has to be done quickly, because also the atoms that are already on the film sputtered off still decay with the same rate, right? So everything must be done kind of in a hurry to beat the half-life time of your isotope. So that means that it's also a very, I mean, it's more elaborate and more time-consuming for anybody to do these experiments, because you have to travel to Switzerland and you have to spend time there doing the measurements. But this is the only way one can really use radioisotope diffusion coefficient measurements with radioisotopes that have a short half-life time. Any questions? And this is then if you don't have radioactive isotopes, but you just apply the normal isotopes, meaning stable isotopes that do not decay, but still they would have a different number of neutrons in their core of the atoms as compared to the most abundant natural isotope, stable isotope, which is the material, how it's listed in the periodic table. And so we basically then have again the sample, and we again use sputtering by ions as both a way to section, because you basically again create a sputter crater, so you dig deeper and deeper into the material. And here you basically have two ion sources to sputter. One is just to create the crater depth, and then this bismuth ion source is used as the analysis beam to basically sputter off then the materials which just enter the extractor and basically go through the mass spectrometer, which is a time of flight mass spectrometer. So nowadays you can not only measure how many of the stable isotopes that you put on top of your material have diffused in, but you can even do some reconstruction on how they were situated in the volume. Certainly not with the same accuracy as atom probe tomography, but still it's valid if you just want to visualize how maybe your diffusion profile on a scale of nanometers looks like. It's not giving you atomic resolution, but it's giving you resolution which is on the 10 nanometer range. So it's very useful, and it's much more easily applicable, obviously, because you don't need to have a radio tracer lab with all the safety precautions for handling radioactive isotopes. Yeah, so these are the measurement methods, and you see some of them are more involved, but many of the devices are found in almost any modern research institution, that, like IIT. I mean, I guess there are several TOF sims probably run here in the chemistry department or maybe also in physical metallurgy. There are also service providers like companies who would do the measurement for you if you don't have the device in your own institution. You have to pay, obviously. Or you find a colleague who's interested in the research and who has this instrument, and you collaborate and put him on the paper. Yeah, so this is all there is to it. This is a little bit elaborate in terms of the steps you have to do, but it becomes routine. And I think as a PhD student, the golden rule in our lab is 1 diffusion coefficient per day. This is kind of what you should aim at when you have really mastered all the methods that you need to apply. Yeah, let's come now back to high entropy systems. Selection of elements, methodology, and preparation techniques. And first we have to worry about simple things, as always. This is a binary alloy phase diagram, and it basically shows you characteristic temperatures for phase transformations as a function of composition of the binary alloy. Right? So you have a liquid phase here, and then there is this 2-phase regime between liquid and solid, between the solidus and the liquidus line. Then you have a huge phase field here, where you have a solid solution, which is stable, but then you have also other phases with other crystallographies present. Now, if we have 2 components, we can use a piece of paper or a screen to display all information necessary, right? To select, for example, a composition and a temperature to obtain a certain phase or phase equilibrium between different phases. If we have a ternary alloy, obviously we have already a difficulty because we have 3 components and we have temperature in order to get the same information into our diagram. So the diagram would be a trigonal prism. It would be a prism which has 3 sides. And temperature axis would point up as the long z-axis, and this would be in xy plane. And you see that normally what we do, because we don't want to carry prisms around, is that we basically do isothermal sections. So we basically have a fixed temperature, and then in the Gibbs triangle, giving all compositions possible in the ternary phase space, the phases present at this temperature in these compositional ranges are given and listed. And so we need to do many slices in order to get the information on which phases exist at which temperature. So the full information which is contained here in this 1 phase diagram would be in as many slices at different temperatures as you need. Let's put a very simple phase diagram here. Binary. This is a simple eutectic, right? How many phases coexist at maximum? What about this point?
Yeah,
3, yes. Yes, liquid plus the 2 crystalline phases coexist, but only in 1 singular mathematically defined point. So it means you cannot vary temperature or composition and still maintain 3-phase equilibrium. And this is determined by Gibbs phase rule, right? And this looks like this. The number of phases that coexist in equilibrium depends on the number of constituents. And the number of degrees of freedom. So it means if we are, for example, in this point, then we are having n equals 2, which is the constituents A, B. We have phases equals 2, right? Because at this point we have, when we draw the conode, solid alpha and liquid, which means we have what does it mean? I can vary temperature or composition. I don't leave this equilibrium. It will be still the two phases which are in equilibrium. And I can vary temperature or I can vary composition, and so on. So it means, obviously, when we increase the number of constituents, we have to recognize that the number of possible phases can increase much. And not only the number of phases in a phase diagram, but the number of phases that can coexist in equilibrium. This is the important point. Many of these phases we don't know, so it can be interesting if you work in multidimensional phase space. So it means one has to have a good way of kind of displaying the phase diagrams and the phases and possible phase equilibria in your multi-dimensional, multi-component alloy. Especially when we are talking about high entropy systems, we talk about multi-principal alloys, right? So it's not that you have a dilute solution of 10 elements in one major element like in steel. No, you have many 5, 6 components which have almost equal concentration. And that means you are going to the center of this multidimensional phase space, phase diagram. And that means you should know and should worry about all possible phase equilibria present and about how to display them. Principal problem here is you need n-1 spatial dimensions to map n-dimensional alloys at constant temperature and pressure. So for a quaternary high entropy alloy, you need 4 spatial dimensions, which is difficult for me at least. Maybe you guys can do it. To imagine, right? I mean, how to have a 4-dimensional space used and how to map it on a 2D sheet of paper. There are, however, some things people have suggested to visualize phase space for 5 or more components. The first one is shown here. So you basically have the 5 vertices. So these are the 5 elements you put together. And you put them on this geometric body, which basically includes the 5 vertices. So these are the elements. And then, since this is again a 2-dimensional or quasi 3-dimensional representation of a 4-dimensional phase diagram, we have to think of this as as a binary phase diagram projected onto a line. So, you know, this is basically from a little bit like graph theory, how you can transform from higher dimension information from in higher dimensions onto a lower dimensional surface. It's a hypersurface, so it could have curvature or be flat. In quintessence, this means this figure could be used to represent some features of your multidimensional phase space, like which phases would occur maybe on the ternary lines that are shown. But I would say I have a problem with a binary phase diagram projected onto a line. Then I do not get much information out of it. It's maybe in computer coding you could project and hide it into it, and then you basically project down to even lower dimensionalities, and then you can see it. But as of such, I would say this is nice for mathematicians, but not really useful for material scientists. A little bit more useful and a little bit more complex is the way shown here. So here all the phases that are known, the vertex phases, meaning the pure elements, as well as the known intermetallic phases, are represented by individual points. And here you see that the vertices are by these circles which are empty, and the filled circles are for the intermetallic phases in this cobalt, iron, nickel, manganese, chromium system. Now you basically arrange these points in this representation at random. So where they are situated in this representation doesn't tell you anything about real alloy composition. It's just the connecting lines that carry the information, because the solid thick black lines show these continuous solid solutions between the phases that are connected. What does that? No. Yeah. These are the vertices. Intermetallic phases, meaning these are compounds which have a defined stoichiometry. So let's say you mix cobalt and iron, and there will be a certain structure which is different from pure cobalt, which is different from pure iron, but it only exists if you have 3 cobalt atoms and 13 iron atoms coming together. So in the phase diagram here, it would be something like a line compound. It could also have solubility, but this is what is meant by intermetallic phase. So it's a defined stoichiometry, and it has its own crystallography, own stability range. Positions are distorted, and you cannot read any. These thick lines, it's a continuous solid solution, meaning you can mix nickel and cobalt in any proportion, and it will basically not form a new crystallography in the solid state. And The thinner lines are connecting phases again, maybe going to the binary. So you have here a two-phase field. Right, so when you are at any point here, you do horizontal, which is called co-node. It connects two phases, this alpha phase here, and then this solid solution phase. Meaning at this point, you have two phases in equilibrium, coexisting. You don't have here in this hashed area a separate phase, you just have the two. If you change the nominal composition along the line, then you will change just the abundance of one or the other phase, but the phases stay the same. And this is meant now with this connecting line. So this line connects alpha and solid solution, and this one here connects cobalt manganese with cobalt. So there's along the line always two phases that coexist. Yeah, so the complete solid solution phase is not shown here. And again, you would not be able to read any phase compositions or any amounts of the phase fractions from this type of representation. It just tells you which phase equilibria are generally present in this system. This is maybe the best way of doing it if you want to do it the hard way. It's basically using line diagrams where you connect a lower dimensional polyeder. So you have a 5-component system, you create a 3-dimensional phase diagram, and now you connect any point inside of this volume to the vertex which is not included in your volume. So 5 components, A, B, C, D are here, E is over there. And then basically you can map out different concentrations according to the distance between pure vertex and the connecting point. And you can do this now to any point in the volume of your A, B, C, D, E. And obviously you can also create different volumes here and connect to a different vertex. So you can basically create a ray diagram for all possible combinations, and that will actually, in the end, mathematically, it's necessary that it can show all the phases and all phase equilibria. Nobody has done it so far in reality, because it's just too complex and too much information necessary. But just this would be something, which would be feasible. How to do it in reality? Do you have a suggestion? I like 2D sheets of paper which I can carry around, or 2D screen to show something. So in order to use it, really, you need to have something which comes in handy, which can be used much more easily than these complicated things. And this is why we use isoplaths. So an isoplath is not a phase diagram. It lacks specific conditions and that are necessary in order to really have a phase diagram. But it shows you very nicely what happens if you keep 4 components at the same ratio. So for example, for the Cantor alloy, you keep cobalt, chromium, iron, and nickel always having the same concentrations. So it could be cobalt 1, chromium 1, iron 1, manganese 1 atomic percent, or it could be cobalt 10, chromium 10, iron 10, manganese 10, but it's always that they are the same. So you treat this as one constituent phase, putting it on one end of your isoplath, and then you just show how the phase equilibria vary when you vary the 5th component, in this case the nickel, from almost 0 up to full 100%. So obviously when nickel is 100%, these guys are 0, everybody is 0. And for example, if we have nickel 20% as indicated by this dashed line, then all of the 4 others would also be 20%, and we would have the full real counter alloy. Right, so 5 times 20, 100, everything's fine. This is much more useful because you can now do a variation. You cut basically a plane through the higher dimensional phase diagram, and you obtain information you need in order to do alloy selection by just choosing, do I want to have a single phase alloy? Then my nickel concentration must be having a certain minimum amount, because otherwise I get into 2-phase regions or multi-phase regions. Yeah, and also it shows you nicely, if you have selected your alloy composition, what is the temperature ranges you want to avoid if you want to avoid either melting or second phase formation, which is happening here in the lower temperatures. Right, so these are all different phases which would form. Some of them you don't want to have in your material at all, because sigma phase is again an intermetallic compound, so specific stoichiometry. It's very brittle, so when you have it in your material and you deform it, your material will probably break. So you don't like it. It's a very big problem also in steels. So the backdraw is you can only show what happens when you vary one element independently. You cannot show in these isopleth diagrams what happens if 2 or 3 elements are varied at the same time. And you cannot read phase compositions or volume fractions of phases from these diagrams. So as I said, not proper phase diagrams, so this needs to be calculated then separately. But I think this is very useful for the real work. No, absolutely not valid. Yeah, lever rule is just the way to calculate phase fractions from phase diagram, and this cannot be applied here. Then we also in alloy selection have to get a more realistic description of the thermodynamics. Very often you see that people like the regular solution model. So solution models basically are describing mathematically what happens if you mix one given element with 1 or 2 or more constituents. And basically the effects of entropy change and enthalpy change are then accounted for, and they are basically related to specific simplifying assumptions, like for example, atoms would behave like billiard balls, so there is no interaction parameter between them, and then it's called an ideal solution. And if you say, there is some interaction, like for example, if I mix one atom into another, maybe heat is generated, or maybe the volume changes from the way you macroscopically calculate, then a regular solution model is applied, which has an interaction parameter in enthalpy and not in entropy. And you can then basically make a series of more and more stringent assumptions to get to any complex solution model. And the thermodynamically adapted power series is the most complex one, but it's basically also then a curve fitting routine, because you have so many parameters that there is no physical meaning related to each and every parameter anymore. Problem is many literature works, people in the literature use the regular solution model, which is the second most simple one. It just tells you the mixing entropy is just statistical, meaning that you calculate the entropy like you would calculate if you draw a ball in a lottery. And the enthalpy of mixing is small, could be positive or negative, but it's a small value. And this is shown here, right? So you see that the enthalpy of mixing, and these authors didn't put the delta here, so I would put the delta H because it's an excess energy, and also for the mixing entropy, they put like this. This is nice for any high entropy paper because the entropy is dominating, right? Mixing entropy. But that's not the reality. Reality is that most of the solid solutions we form are rather more, at least of the sub-regular solution type. So it means that the interatomic interactions are not symmetric to equiatomic composition. It's different if you are the A-rich side as compared to the B-rich side because the A and B atoms are sufficiently different. This is why we have to take into account that these curves for temperature times mixing entropy or for the mixing enthalpy are also asymmetric. So it means that at least a sub-regular solution model should always be checked if it does not fit the data of your material better than a regular solution model. I know that many students shy away from this because it's more work, but it really is giving you extra insight and a much better. To use the Midema model normally, maybe I come to this in 2 slides or so. Maybe I go there first. Here. So when we use these parameters like lattice distortion or like mixing enthalpy, then as you said, right, for binary systems it's clear because A, B, B, A, there isn't any more. But for ternary already it's getting more complex. For 5 it's highly complex. And this is why people basically went and designed approaches which are based on either atomic size differences which are averaged out, or in this case when you think of the mixing enthalpy, which go back to these values which are for the binaries. So these are the binary interaction parameters basically, and you then just calculate the average to get an effective value for the n-component solid solution. This is simplified, and this is a better way. So what you would get really is data which are calculated by Midema's model. There you can get for the binaries the real interaction parameters out of them in the real. It's still an approximation. It's a continuum approach, and it's not rigorous, but it's empiric. But it is very good, and it works. And then you calculate these interaction parameters, and then you basically use this summation to get, again, the average effective mixing enthalpy for the n-component system. Obviously, you can have now different situations. You can have 5 components where some of the binary systems show a positive enthalpy of mixing. That means they like to phase separate. And some of them could have a negative heat of mixing, which means that compound formation or mixing is favored. In these cases, this averaged effective value will depend a lot on your composition, your nominal composition, because what you do is a weighted average in the end, right? And then it is, yeah, it's not complicated, but whether your result will be very good in terms of comparison to reality, it's unclear. There could be situations where this is not the case, but again, then you are probably in a case where the sub-regular solution model would not be the best. You would probably need to go to a much more complex solution model because maybe one of your constituents at least is so much different from the others that it creates these very large positive or negative mixing enthalpies. And then, yeah, one probably needs to go to real Kalfat numerical modeling and not use these analytical descriptions of the solution models. But if you have only positive or only negative, or if there are changes of the sign, small magnitudes of the binary interactions, the binary mixing enthalpies, then this is basically giving you a very good description. So in all cases that I know, it has been valid. Yeah, what I wanted to say here again is be also careful again, especially for the entropy. We like to use only the statistical entropy of mixing, right? So calculate how many different configurations can we have when we add a different particle into a given configuration. So it's what we call complexion number. It's the number of distinguishable different configurations. But there are also different sources of additional entropy: magnetic entropy, vibrational entropy, and all of these could be, especially the vibrational entropy, much larger than the mixing entropy. And they could also depend a lot on where you are in the phase diagram, as shown here. So you could get very, very strongly asymmetric courses of these entropy functions, which means that your mixing entropy, which you calculate in this ideal way, might be dominant and might be insignificant in other cases in the same only binary system. And now you have to imagine that this is for the 4 or 5 component system, right? So it means one has to be always a little bit careful and really get a good description of the thermodynamics, because in the end, the thermodynamics will also be directly related to the diffusion measurements you do. Yeah, so thinking of phase formation and phase stability, obviously this is the governing equation here, and we have discussed this already. In this term delta S mix, all these configurational, vibrational, electronic or magnetic contributions need to be taken into account. And obviously we also have geometric effects, like the size of an atom. The size of an atom is something which is highly undefined by nature, because it will change whether you put this atom together with equal atoms and form a crystal lattice, or whether you put this atom as an impurity into a different lattice, because the electronic interactions will be different, and that means the effective radius will change. But these are really very important geometry effects, and I think you all know Young-Rodary rules for binary solutions. If not, I will come to them shortly. One has to take into account both aspects have always to be considered in order to make a good high entropy system, to have large solid solubilities. Yeah, I went through this already. Young-Rodary rules. These are rules for either defining ranges where you can find certain intermetallic compounds or phases. Then the electron per atom condition was used. But for this case here, more importantly, is this geometry effect, the atomic radius. So if you want to mix 2 atoms and they should then form a solid solution, mix on the same crystal lattice, then the atomic radius difference should be less than 15%. Also, the crystal structures of solute and solvent should be similar. Doesn't mean it should be identical. If you think of the Cantor alloy, out of chromium, iron, manganese, cobalt, and nickel, the whole alloy is FCC, face-centered cubic, but only 2 components are FCC, right? But the crystal lattices of the other constituents are not that much different, so they are similar, they are related. And then the same valency is also of the solute and solvent is also helpful in order to create solid solutions as well as similar electronegativity, because otherwise you get directed bonds. So coming from Hume-Rothery rules, people have thought a lot about different conditions on how to select elements to make high entropy systems. Difference in electronegativity, and always now you have to kind of think of this as getting more complex when you have 5 elements, right? So you have to define how to calculate these parameters, or at least estimate these parameters for a 5-component system. And so one always has these average values, like here, this is the average, the weighted average of electronegativities. Yeah, valence electron concentration, you just add up. E/A condition, the average number of itinerant electrons per atom, is not really applicable, because the amount of itinerant electrons depends, first of all, on the binding, and second of all, for transition metal alloys, you have s, p, and also d orbitals. And how many of the electrons from the d orbitals actually contribute is not so easy to calculate. Right? So it means how many do you count as the ones which you put into the E/A ratio? If you, for example, look now and think electrons per atom ratio condition is the same as valence electron concentration condition, then actually if you do the calculation for pure copper, you would see that the electron over atom E/A ratio condition gives you 1.
But D element, D is still surveillance.
Yes, but they are not counted for the E/A, but they are counted for the valence electron concentration, because there all the atoms, like you see, there is 1 s electron, a 4s, and there are 10 d electrons, the 3d10. And so valence electron concentration gives you for copper an 11, and E/A ratio condition gives you a 1. What is the physically meaningful value? I would say it depends. It depends on with which element you mix the copper. Right? So this is difficult. And this omega parameter condition, there are also several variants of this out there in the literature. Basically combine, again, something like melting temperature differences as well as mixing enthalpy and mixing entropy, both in a numeric parameter, one number, which basically gives you, yeah, they all calculate at the melting temperature, and that's a big problem, because when you come from the liquid and you cool, you go through a region where the temperature obviously is high, while the crystal is the stable phase. A high temperature means the term temperature times entropy is large, and it's highly likely that this region here of higher temperatures is giving you conditions where a solid solution phase might form. But if you go lower in temperature, obviously the T times S term gets less dominant, enthalpy becomes more dominant, and it means very often you go through a region where you have solid solution only as a metastable phase, which is in competition with another phase that forms and destabilizes your high entropy system. There's one thing also concerning electron negativity. You can calculate it in different ways, and you get quite different regions where elements have similar conditions, similar properties, so that they would indicate good solid solution formability in these regions. If you look into it, you would think, oh, maybe then manganese should not be part of the Cantor alloy system, right? Because it's not so closely related here than the other ones. So my feeling is, and this is a personal feeling, I wouldn't trust all these electron negativity, valence electron concentration, E/A ratio conditions for high entropy systems. This is also shown here in this nice plot, where basically as a function of valence electron concentration, people have plotted a number of alloys, which are either in BCC or in FCC or in a two-phase mixture, FCC plus BCC mixture. Fully closed symbols are for only FCC phases, fully open for only BCC phases, and these half-filled symbols are for the mixtures. If you look at it, these are rather similar systems. So this is not displaying all kinds of families of high entropy systems, but just different compositional variations in a few families only. And still one can say that with the exception of maybe two or so, all of them are not really showing distinct behavior. So yeah, my opinion is there are no correlations found between phases formed and this electron negativity or valence electron concentration condition when you really compare a large number of different alloys and the range of alloy families. The solid solutions, intermetallic phases and multi-phases with solid solutions, intermetallic CCAs, so high entropies, which are not only one single phase solid solution, all have very similar ranges in these parameters. So look at the thermodynamics, mixing entropy, and the rest, I think, is not really helping in terms of making alloy selection in a meaningful way. What can happen if you choose the wrong composition, if you wanted to have an alloy which is composed of only one solid solution phase, are mostly two mechanisms. It can undergo spinodal decomposition. So it means there is a very high positive mixing enthalpy, and that basically makes the free energy functional of your solid solution convex, and the convex functional for a single phase can never be stable. That means it's separating automatically, you cannot prevent. It's an unstable condition, not a metastable, an unstable condition. Every fluctuation will serve to go downhill, meaning precipitates will form, two phases will form, which have different compositions. Or obviously precipitation, right? So you could get a new phase. This is often very nice because it might impact your mechanical properties in a very good way, because you have additional ways to stop dislocations. The grain boundaries can be pinned. But if you want to make a high entropy alloy really consisting of only a solid solution, then it's not what you want to get. So one needs to be careful. And this is affected mostly by the formation enthalpy of this intermetallic or second phase. So this will overrule temperature times mixing entropy at some point, and then you can not avoid that these guys are formed. And mostly they form first at the grain boundaries, because there is higher mobility, and also the accommodation of a new phase can be easier when that phase is still very small, the nucleating stage. So stresses are not as high, and stresses give you an additional free enthalpy penalty. So adds up to the height of the FD activation barrier, and this is why these places, dislocation cores, grain boundaries, are preferred nucleation sites for the second phases that form, which can be used to your advantage. Because
in normal system, like we want to prefer, because most of the elements aggregate there.
yes,
But in HEA cases, like most of the elements are mixed in the whole system. Like it should be, I think, similar to.
maybe think about it this way. So with each grain boundary, you have the so-called linear grain boundary expansion. It's a parameter measured in meters or so, but it basically signifies the additional excess volume associated with this planar defect. More volume means diffusion can occur more easily, but more volume also means any foreign element can go there more easily. And if you have nucleation of precipitate, then the nucleation stage has the highest activation barrier. If the nucleation is successful, growth can occur much more easily. And the nucleus size is of the order of maybe a nanometer, maybe 1.5 nanometers. So it's very small. So it means that the grain boundary provides really a good way to accommodate this different structure, the different specific volume of these new phases forms. So whether it's high entropy or conventional alloy, the grain boundaries will be the preferred sites. Okay, great. This is for tomorrow. If you have questions. So, thank you. So, see you tomorrow.